Okay, so let's pick up where I left off. I'll have to pick it up a little bit because I want to get onto stochastic gradient and cover at least most of that today. So I have a little bit more to say about gradient methods that work with, at least normally work with exact gradients, because there are a few more interesting things to say. One of them is this idea of accelerated first order methods. So the idea here is much the same. It has a little bit of the same momentum idea as came into the heavy ball and conjugate gradient methods, but it's expressed a little bit differently. One difference is that instead of generating a single sequence of iterates, like xk, xk plus 1, xk plus 2, you actually generate two sequences and they sort of hopscotch each other. You generate the next element in the y sequence and the next element in the x sequence and so on. And if you look at the formulas of these things are very mysterious, and the analysis is also quite mysterious, although quite elementary. It doesn't use any deep math or anything, but it's very intricate and tricky and so on. But the idea is that to get from the latest y iterate to the next x iterate, you do exactly the sort of short step gradient search that I told you about earlier. Okay, this was the one that we analyzed in the hour before lunch. So that part is not mysterious. But the next part is where you calculate these constants alpha k and beta k. And I won't even try to explain what's going on there, except to point out that the condition number comes into the formula. So these are recursive formulas for getting alpha k and beta k. Then the condition number comes in there. And then you use the beta k that falls out of that to get the new y from the latest x. And there's a bit of momentum coming in there, because you can think of this term as being kind of a momentum term. So in a sense, the gradient part of the step is sort of separated from the momentum part, but the effect is a little bit the same. Okay, so I showed you that picture already. And you can get this kind of convergence result. First of all, these methods work whether or not the problem is weakly convex or strongly convex. If it's weakly convex, then this kappa is infinity. The condition number is infinite, so this term here is always 0. And things simplify a little bit, but it's all still valid. In that case, you get a 1 over k squared type convergence rate. That's what you see there. But in the case where you know what kappa is, you have a good bound on the condition number, you get the sort of convergence rate that we saw in the for the heavy ball and conjugate gradient type methods. This rate that's sort of related to 1 minus 1 over root k. Okay. So in a sense, you sort of get the best of both worlds combined into a single method. And by the way, the beta, the relative size of the gradient the relative size of the momentum term and the steepest descent term is a little bit similar to what you see in heavy ball. There's much more emphasis on the gradient, on the momentum term. It's close to 1, just like was the case in the heavy ball approach. There's another method that I just mentioned just quickly. It's very similar in spirit, called FISTA. It was developed. Part of the reason I'm mentioning is that some of the work on this was done at IPAM when Tabul was here on sabbatical in 2010, although the original work was done earlier. But it's very much a method of the same type. You'll see a steepest descent step here and a momentum type step here, and very similar convergence rates. Maybe the advantage of this one, I mean, the only difference is the way the constants are calculated. Maybe the advantage is that you can read this paper, the 2010 paper, where all the analysis is done in 2 or 3 pages, and it's all self-contained. So it's sort of fun to read. None of it is very intuitive. It's all just very technical, kind of accounting and messing around with equalities and inequalities, but anyone can follow it. So the last thing I wanted to mention, or one of the last things I want to mention before we leave the idea of gradient methods, is I want to return to that picture I showed you earlier of steepest descent, just the step with the negative alpha k, negative gradient direction, applied to that quadratic that was ill-conditioned, where you got the iterate zigzagging back and forth across the valley. So that's like the top picture here. That's the same picture I showed you earlier. So there's a class of methods that sort of breaks all the rules, and by the rules I mean, you know, the intuitive thing to do is that on every iteration we try to do better than the iteration before. We try to get an improvement in the value of f, right? So we're always going downhill. So the class of methods due to Barzilai-Borwein, where they throw that out the window and they sort of say, well, what happens on a single iteration isn't all that important. What we really want to do is we're interested in sort of the long-term convergence behavior. And even if that means putting up with very large function increases over a single iteration. And so they've got this very beautiful paper in 1988. It's quite old and it's quite short, but it has this very offbeat convergence analysis that's like nothing, as far as I know, that had ever been seen before in optimization, where they analyze a special case of a two-variable quadratic function and are able to show that with very high probability, in the long term, you get much better convergence than with a standard gradient descent method. But the idea is, again, it's a method of gradient descent type, but the way you choose the alpha is completely different. You basically choose an alpha that it is kind of in the spectrum of the inverse Hessian. So as we'll see, or as Nesterov will talk about later in the week, he'll tell you a bit more about Newton-type methods. In Newton-type methods, the search direction is not the negative gradient, but it's the negative of the Hessian inverse times the gradient, okay? And the reason that's interesting is that that step with the Hessian inverse is the one that minimizes the quadratic Taylor series approximation. And it has much faster local convergence properties and so on. So the disadvantage, of course, of Newton's method is that you need to know the Hessian or some approximation to it. So Barzilai-Borwein, you can think of it as saying, okay, I'm just going to approximate the Hessian by a scalar times the identity, okay? And how do I choose the scalar? Well, I choose the scalar till I somewhere in the, at least has a value in the right ballpark. In other words, it falls somewhere between the smallest and largest eigenvalues of the inverse Hessian, okay? So their order is reversed here because I'm taking the inverse. And the way it does that, well, there's actually not a uniquely defined way, but there's a variety of ways it does it. Essentially, it looks at the last step. It looks at the difference between the last two x iterates and the difference between the last two gradients. Now, Taylor series will tell you that zk is approximately the Hessian times sk, all right? The Taylor's theorem will tell you that. And so it says, okay, let's pretend that's the case, and let's find the value of alpha that sort of makes zk look a bit like the Hessian of sk. And one way to do it is to solve this little least squares problem, okay, scalar least squares problem. It's not the only way, all right? But they all give you a value in this range. And then you just use that alpha. Now, it might turn out that that gives you a tremendous increase in the function value. And in fact, and it can give you very dramatic, you can easily code this up, you know, in 10 lines of MATLAB or maybe 20 lines and try it out on a quadratic function, and you'll see this very strange behavior. But if you look even at this simple picture, it's not implausible that it might work, okay? Because suppose you start here in the same place as you did in the greedy sort of steepest descent, and suppose you dramatically overshoot the minimizer along this direction. You go off into the stratosphere here. Now, next iteration, you're going to be again moving in the direction of negative gradient, but it's possible that if you stop in the right place over a span of 2 steps, you're actually going to make much more progress towards a solution than you did in a span of 2 steps here, right? And that pattern could repeat. And in fact, you do see it repeat. If you try it on just 2 variable problems, or actually even on n variable quadratics, you'll often see this kind of, if you take 2 steps at a time, you're making significant progress. And the amazing thing is that they're able to analyze this, and in the original paper, a lot of people have worked on this since and have kind of extended the analysis in various ways and found connections in the literature going back into the 1950s, and this paper in the Japanese literature. And it's all very interesting and very original, and sometimes it works pretty well, okay? So we've tried it in various codes for compressed sensing and found that it gives some advantage. So I just thought I'd mention that. It's something that's very easy to try, and you know, sometimes it is an appropriate thing to try. Okay, so just a slide or two on a method that's going to come up again, I think tomorrow when I talk, and that is this idea of averaging to try to improve or make the convergence more robust. So there's a quite recent paper by Nesterov where he introduces this idea of Primal-Dual Averaging. Well, the idea has been floating around a lot in the literature. And part of the motivation for this is that if you're doing well, is first of all that it extends to the stochastic gradient case very well, okay, as we'll see later on. But the idea basically is you take sort of a linear model of the objective, just like you do when you're doing steepest descent. In steepest descent, you're taking the first order Taylor series approximation. Well, here, instead of setting the gradient to be, of that first order approximation to be the most recent gradient, he basically averages over all the gradients you've seen so far, okay? And uses that as the gradient, as the linear term in the approximation. And then to make the whole thing well defined, he needs to have a quadratic term to stop you moving too far. And he basically has a quadratic term centered at the initial iterate and takes the new iterate to be the minimizer of that linear approximation with the average gradient and this quadratic term, okay? Now the trick about the quadratic term is it's multiplied by a coefficient that is gradually, as k goes to infinity, this is going to 0. And so the weight that's put on the step by the quadratic term kind of fades away. And it just kind of converges more and more to a sort of negative of the average gradient. And as you're converging to a solution, of course, the average gradient will eventually converge to the true gradient the further you go along and the closer the iterates get to be together. The main advantage of this, as I'll explain later, is that it still works if you're dealing with non-differentiable functions where you just take the individual gradient terms to just be members of the subdifferential, and that's already an advance on steepest descent, where steepest descent is not guaranteed to give you a function decrease if you just take an arbitrary member of the subgradient in the non-smooth case. This is guaranteed to work eventually. And the other thing is, as we'll see later, you can extend it to the case where this is only an estimate of the gradient. Now he also, I call it Primal-Dual Averaging. This part is averaging, in a sense, dual averaging. It's averaging the gradient. The other thing that he does in that paper, and this is again an idea that we'll see in other algorithms quite soon, is that you don't take the latest x iterate to be your best guess of the solution. Instead, what you do is keep a running tally of the average of all the x iterates you've seen so far, and you use that as your estimate for the solution. And this again tends to have sort of smoother, less erratic behavior than the individual elements of the sequence. And you can prove that in some sense it's a more well-behaved estimate of the solution. And I'll give you a proof later on in the context of a different method that illustrates that. So Nesterov is able to show that for this method, he actually analyzes a more general class, but this is one of the simplest special cases that falls out. He's able to show that the function values converge like a 1 over square root of k. So that's a slower convergence rate than we were getting for steepest descent, right? But it turns out it's got other advantages, mostly in the sense of being more extendable, as I mentioned before. You can extend it to the non-smooth case and to the estimated gradient case. So we'll see more of this later on. One of the criteria that I used in selecting methods to talk about in the gradient method domain was that as I said right at the start, I was sort of interested in methods you could extend to more general settings. So first of all, let's think about how you'd extend some of these methods to the case where you want x to lie in some constraint set, omega, where it's omega, say, a closed convex set. So is it easy to extend some of these methods to that case? All right. Well, let's start with a method that I just talked about, this Primal-Dual Averaging idea. How would I change the step calculation if I suddenly had a constraint to deal with as well? Well, formally, the change is very similar, is trivial. All I do is take the subproblem, which I have to solve to get the new value of x, and just add the constraint x belonging to omega to the subproblem, okay? So formally, it's a trivial change. Practically, it's also, in the case where omega is a simple set, it can also be trivial. For example, if omega is a box, if it's just, you've just got upper and lower bounds on each component of x, it's very easy to write down a closed form solution of this problem, okay? Or if omega is a ball, it's easy. In cases where omega is a general convex set, it can be much harder, okay? But there are many special cases where it's not hard. The same thing is true of that accelerated Nesterov gradient method that I showed you earlier. So you remember this is the one where I had the x and y sequence, and I'd take a steepest descent step to get from y to x, and then I'd do this stuff, and then I'd do this momentum step. Well, this is exactly what I had 5 slides ago, except that this line has changed. Instead of just saying xk plus 1 is yk minus 1 over L times the gradient, I changed that into a little subproblem in which I constrain I constrain xk plus 1 to be in the set omega. Okay, now if this constraint was not here, the minimizer of this least squares problem is simply exactly what I had before. The minimizer is going to be y equals this stuff here, which is exactly what we had before. So all you do is restate it as a minimizer and then just add the constraint. And the convergence theory basically goes through without any changes, okay? Right, so, you know, that algorithm is easy to change. FISTA is easy to change, okay? So we know how some of these methods can be extendable to constraint sets. Let's talk about another kind of change that is, again, interesting in the kinds of problems that you guys are interested in solving, and that is where you take the function f and you add on a non-smooth regularization term, like an L1 norm or something like that, okay, to induce sparsity or some kind of structure. So these methods that I told you about, how can they be modified to this situation? Well, some of them can be modified quite easily. For example, let's take that, the very first method we talked about, which was the short step steepest descent method, where you just define the new iterate to be current iterate minus 1 over L times the gradient. So how do I deal with that now that I've got this non-smooth term? The gradient's no longer defined, so what do I do to fix it up? Well, what I do is I approximate f in exactly the same way as we did earlier, but then I add in explicitly the regularization term. I add it into the subproblem that you have to solve to get the new iterate. I just explicitly add it in. So if this term were not here, this algorithm would reduce to the one that I had earlier at the, 10 minutes into, or 15 minutes into the last talk, okay? But if I just add it on explicitly and now define the next iterate to be the solution of this problem, again, a lot of the theory will go through and you can prove many of the same kinds of results. So the question is, can you solve this subproblem reasonably economically? And the answer is that depends on the nature of this function phi that you're adding on. And again, there are a lot of interesting cases where you can solve this cheaply. For example, if phi is the L1 norm, which is sort of everyone's favorite case of a regularization, again, you can write down a closed form solution to this problem. So it's no more expensive than doing the standard steepest descent step. You need to evaluate a gradient, you need to do order n arithmetic, and you're done, okay? So again, and we'll talk about that more tomorrow, about this class of methods. Okay, so here are a few references that talk about some of the methods that I've mentioned, and I've referred to a few of these during the course of the lecture, so I just put them there for your reference if you're looking at the slides. Okay, so let me start the second part, which is, are there any questions on the first part? Feel free to interrupt anywhere, by the way. Yes, down the back.
Hi, simple vocabulary question. The word shrinkage has come up now a couple of times in these lectures. Could you just expand a little?
Sure.
Thank you.
I'll actually say more about it tomorrow. It sort of comes from the case, on this special case where this is the L1 norm. So it's shrinkage because the presence of the L1 norm tends to draw the solution of the subproblem closer to the origin than it otherwise would be. If you just took the naked steepest descent step, it would lead you to a certain point. The fact that this term is there tends to either bring you right to the origin or tends to move it back toward the origin. So it kind of shrinks the norm of the solution in a sense. Okay, that interpretation may not necessarily hold when you have other kinds of regularizers, but it certainly holds for L1. So you can think of this process as actually taking the steepest descent step and then shrinking towards the origin. Okay? Any other questions? Yeah.
All of these results are derived in the case of a quadratic, and thus obviously very convex loss function.
No, not all of them. They're mostly, the theory for most of them is a smooth, just smooth F, but I've kind of specialized it in places to the quadratic.
What happens to these sorts of techniques if you have a non-convex?
Yeah, okay, the $64,000 question.
Oh, okay.
So you can say some stuff. So for example, when I started talking about line search methods, I had those three alternatives. The one that where you try to do an exact line search and you aim to satisfy those two conditions. So that all is analyzed in the completely well in the smooth non-convex case in chapter 3 of this book. And we sort of prove things like convergence to stationary points and so on. So that all goes through. The backtracking scheme will continue to work in a non-convex case, and you can still prove convergence to stationary points. What doesn't necessarily work are those short step methods, because they kind of presuppose, and the analysis for those sort of presupposes a convex function. So you can still run those methods in the case where you only need the upper bound, not the lower bound. You can still implement those methods and they'll do something, but I'm not sure what you can prove about that case. I mean, people do that. People apply stochastic gradient methods, for example, quite happily to the non-convex functions that you see in deep learning. But I'm not sure how much theory there is to go with that, okay? But you can always try it and see what happens, right? And maybe you can say something, but you certainly can't say nearly as much as you can in the convex case. Any other questions? Okay, so stochastic gradient, all right. So again, I'm going to mostly be talking about convex f here, or functions f, and again I'll mostly be talking about unconstrained minimization of f, but I'm not going to necessarily assume anymore that f is smooth. I'm not going to assume that you ever want to evaluate the function value, because you might have to make a complete pass through the data set to do that. But what I will assume is that if I give you an x, you can always give me back an unbiased estimate of the gradient or some element of the subgradient, okay, of f. So that's always assumed. So in other words, suppose the function that you're minimizing is the expectation of another function that depends not only on x, the set of parameters, but also on the random variable. So the function that you really want to minimize is just a function of x in which you've taken the expected value with respect to the random variables. So one way to estimate the gradient of f is to pick a value of xi according to the distribution that xi lives in, and just evaluate the gradient of big F at that value of psi, okay? Or if you've got a finite sum, for example, if f is just the sum over m terms, one way to evaluate the gradient of f is just to pick one of these i's at random and evaluate the gradient of fi, and then scale it by m to get the scales right, okay? So the appealing thing about this is that you can get an estimate of the gradient very cheaply. You might only need to look at one item of data, for instance. And it's still got some signal in it because its expected value is correct, but it might have a huge variance, and there might be an enormous amount of error in it. But you hope that in the long term you're picking up enough of the signal from the gradient that you'll still get some sort of convergence going on, okay? So you may need many more iterations than you might need with a gradient method, with an exact gradient method, but each iteration is potentially much cheaper, okay? So there are many applications of that, and I'll go over these just very quickly because we've already seen some of this. Very often you've got a loss function that's sort of that goes through the data set one element at a time and takes your current set of parameters w and tests how it does on the ith element of the data set and uses that to come up with some kind of score on how good w is on that one item of data. And that might be added to a regularization term. So that happens in SVM, supported vector machines. It happens in logistic regression, right? Just a word on subgradients, because I'm not sure if all of you have a background in optimization or convex analysis. So a subgradient generalizes the concept of a gradient to a convex function. And it's sort of best illustrated by this picture on the next slide. If you've got a function f, which is mostly smooth, the top line here is a function f, it's mostly smooth, but it's got a kink at this point where the gradient changes very sharply. So there are many ways to sort of come up with sort of a gradient at that point. And the most useful way is to take basically all possible gradients at that point. In other words, you take all the planes that are tangent to f at that point and take their slopes and call all of those slopes subgradients, right? So if you're at a smooth part of f, then there's only one tangent to f. And the slope of that tangent is the gradient, and it's defined uniquely. But if you're at a point of non-differentiability, that's no longer the supporting hyperplanes, that is the planes that lie entirely below the graph of f, are not uniquely defined. And so you've got a whole collection or a set of subgradients, okay? And it's a closed set. So algebraically, it's defined like this. So a subgradient is any vector g, such that the true function value at z is greater than or equal to the linear approximation based at x with slope g, okay? So this means that the plane lies below the graph. So that's how you define a subgradient. And it reduces to the regular gradient when f is differentiable at x. And modularity, I probably had this on a much earlier slide, but you can still talk about strong convexity of a non-smooth function, but you can't talk about Hessians anymore because the Hessian may not be defined at a point of discontinuity, but you can still talk about mu as being a lower bound on the convexity, on the curvature of the function, even when you're dealing with a non-smooth function. And it enters in much the same way as it does when you're dealing with a smooth function, except instead of talking about the second order Taylor series approximation to f at the point x, in the first order term you just use any subgradient, okay? So you say that the function is strongly convex with modulus mu if it satisfies this inequality for all possible subgradients. And again, this reduces to the definition we had before in the case of a smooth function. So that's a little bit of notation before we push on. Okay, so the classical stochastic approximation method looks an awful lot like the steepest descent method that we talked about earlier, which just took the negative gradient of f and headed in that direction, taking some step alpha k. The only difference here is that we don't have the gradient of f. What we do have is this approximation. I'm going to denote it by big G, and big G at x and psi is supposed to be a unbiased estimate of the gradient of f at x, okay? And I get it by picking some psi. I'm going to be dealing with this expectation version of the setting of the problem. So I'm just going to pick some psi, let's call it psi k, and evaluate my approximate gradient at that point and take a step in that direction, okay? And how we choose the alpha k is the subject of most of what I'm going to talk about. Okay, and we've got this unbiased property that I talked about earlier. If I take the expectation of this g with respect to psi, that has to lie in the subgradient. All right, so I'm actually going to show you the analysis that proves a convergence rate of this approach for certain choices of the step length alpha, because it really is elementary. Uses a bit of elementary convex analysis, a little bit of elementary expectation stuff, and some very simple inequalities, and it can all be shown in a couple of slides. So don't get discouraged if you don't follow all the math, because you can always go and check these slides later on, but take my word for it that it is pretty straightforward. So this version of the analysis comes from a 2009 paper by Nemirovsky, Juditsky, Shapiro, and Land, which I recommend to you. The early sections of this paper are very easy to read and have a lot of, summarize the state of the art pretty well, I think, certainly for the elementary algorithms. So the thing that they measure here, the thing that they want to converge to zero, is this quantity ak, which is the expected value of the error in xk squared. So again, x star is a solution of the problem. We're dealing with a convex problem, and I take ak to be expectation squared. This expectation is taken over all the random variables that you've seen so far. Now, how many have you seen so far? Well, to get to xk, you need to have seen psi1, psi2, up to psi k minus 1, all right? Those random variables are enough to get you to xk. And if you take expectations over all of those, that gives you this quantity ak. And you'd like ak to go to 0, and you'd like to see, how do I have to choose alpha to make ak go to 0? And how do I choose alpha to make ak go to 0 as fast as possible, okay? They're the questions you'd like to answer. Well, we can analyze this. And again, this has echoes of what I did before. Let's just take the new error squared at the new point xk plus 1. Let's just plug in the definition of xk plus 1 here. And now let's do an expansion. So we'll group xk minus x star, and then we'll put that in one group, and the other group will be alpha k times g. And it expands out when I expand this square 2 norm into 3 terms, okay? Now I'm going to take expectations. And I know from this definition up here that the left-hand side is just ak plus 1. The right-hand side, the first term, is just ak. The last term, what I'm going to assume a little bit more about this gradient estimate than simply its expected value is in the subgradient. I'm also going to assume that it's uniformly bounded. So it can't get too wild, okay? So for all the x's we see and all the xi's that we pick, I'm going to assume this isn't going to do anything completely crazy. It's bounded by some constant, say m squared, okay? So if that's true, I can also bound the last term. When I take expectations, I can bound this last term by m squared, okay? Now what about this middle term? Now remember, I'm taking expectations with respect to all the random variables that I've seen so far, all right? So let's do that with the middle term. Now I'm just going to condition out the random variables up to stage k minus 1. So this notation means, with the square brackets in the subscript, this notation means all the random variables psi1 through psi k minus 1, okay? So I just separate out psi k from everything that came before. And when I take this conditional expectation here with respect to the psi k, I now use the fact that xk does not depend on psi k. It only depends on psi1 through psi k minus 1. So I can actually take this expectation with respect to psi k inside here and just associate it with the g, okay? And then I can use the fact that I know that the expectation of big G with respect to psi k is just an element of the subgradient, which I'll denote by little g. Just an element of the subgradient of f evaluated at xk. So I'm able to simplify the middle term by making this observation, okay? So on the next slide, I just plug in that estimate, and I now use the factor of strong convexity. I've assumed that the function, maybe I forgot to tell you this, but I'm going to assume that the function I'm minimizing is strongly convex, with mu greater than 0, okay? Now a couple of slides back I told you what that meant in the case of a non-smooth function. I said that f of z had to be greater than or equal to f plus g transpose z minus x plus 1/2 mu times z minus x squared. Well, I'm going to plug in z equals x star, the solution, x equals xk, and I'm going to apply that formula for strong convexity, that definition of strong convexity. And I can use that to get a lower bound on this middle term. Sorry, I'm going the wrong way. I can use that to get a lower bound on this quantity, okay? All right, and the lower bound is what I need because that appears as a negative here on the right-hand side. So a lower bound will let me put less than or equal to and continue on with the analysis, right? So that's what I do. So on the right-hand side, I've got the AK term, I've got the term coming from the final bound, and the middle term, I've now been able to bound that using the strong convexity argument by 2 times mu times alpha k times AK, okay? So now, having done all the expectations, I've now got this nice expression that relates the expected error at the new iterate to the expected error at the previous iterate, and it's a function of strong convexity quantity, it's a function of the step length, and it's a function of the global bound on the variance estimate. So I can do something with this, right? If alpha k is small, this quantity here in parentheses is less than 1. So at least it gives us hope to think that we are shrinking. The AK plus 1 will be less than AK, which is great. The only fly in the ointment is this last term, okay, which is positive. So we have to sort of make sure that we choose alpha so that overall AK plus 1 is smaller than AK. We get enough of a decrease here to offset the increase we get here, okay? And there's actually a variety of ways of doing that. Here's one way. You can pick alpha k to be 1 over k times mu, where k is the iteration count. So this is a sequence of decreasing step lengths, okay? Alpha k is shrinking as k goes to infinity, okay? We can prove that this gives you a convergence rate of 1 over k. That is, AK goes to 0 at a sublinear 1 over k rate. Here's the proof. It's only going to take one slide, I promise. we're going to prove inductively that each AK is less than or equal to some quantity Q, which is given here, divided by 2K. Q is the maximum of the initial error squared and m squared over mu squared, where m is the variance bound, mu is the strong convexity parameter. So I'm going to prove this by induction, okay? Induction means I assume it's true for K, and I want to prove the same inequality holds for K plus 1. Here it is. This is the entire proof, okay? So I take that expression, what happens on a single iterate, I plug in the value of alpha k, it's 1 over mu times k. So I just made the substitution here. So 2 mu times alpha k becomes 2 over k. The mu's cancel. The last term I get alpha k squared as 1 over k squared mu squared. So I've got rid of the alpha k at this point. Now I use the inductive hypothesis, which is that ak is less than q over 2k, right? So I've replaced ak by q over 2k here and here, okay? So I get to this line. I now do some very elementary manipulation with this. I get common denominators, I add these two terms together, I do a little clever factorization here, and then I use the fact that k squared minus 1 over k squared is less than 1, right? And I end up with, lo and behold, ak plus 1 is less than or equal to q over 2 times k plus 1. That's exactly what I wanted, okay? So we're able to show that ak plus 1 is approaching 0 at kind of a 1 over k rate. So that's a nice result, right? It gives us the same sort of sublinear rate as we were seeing for the weakly convex case when we had the entire gradient, okay? We're not getting a linear convergence rate like we got when we had the full gradient in the strongly convex case. We're getting a rate more like we saw when we had a weakly convex case with a full gradient. But it's still pretty impressive that we can prove something about in using such elementary tools, okay? Now, we'll say more about this method later, and particularly when we talk about how you might potentially parallelize this algorithm. But before we do, let's talk a little bit more about what happens in the weakly convex case. Remember, I took alpha k to be 1 over k times mu. In the weakly convex case, mu is equal to 0, so we can't do that, right? We can't take infinitely long steps. Moreover, even this method can be really, really bad if you don't have an accurate estimate of mu, right? In other words, if you underestimate mu, if you choose your estimate of mu to be way below what it really is, things get arbitrarily bad. And there's an example in Nesterov et al. Where the convergence degrades enormously if you choose the wrong value of mu. So in this paper, they proposed to fix that up by doing averaging, which I told you about a little while ago in the context of Nesterov's 2009 method. So in doing averaging, you sort of sacrifice the rate of convergence. Instead of 1 over k rate, you're going to get a 1 over square root of k, which is somewhat slower sublinear rate. But what you gain is that you get much less sensitivity to the estimates that you're plugging in to calculate the step. And to pique your interest a little bit, you might have heard the term mirror descent. If you've been going to any of the machine learning meetings, you'll hear a lot said about mirror descent. This approach that I'm about to tell you about is sort of a special case, a very important special case of mirror descent. Okay, so what's the idea? Well, the idea is you take exactly the kinds of steps that we've already been talking about, as you do for standard stochastic approximation. The difference is that instead of taking the latest x iterate as your best guess of the solution, you take this weighted average over all the x's that you've seen, weighted by the choice of step lengths at each iteration, okay? And you report that as being your latest best guess, okay? What are the choice of step lengths? Well, again, there's a variety of ways you can choose the steps. Let's analyze the case where you take alpha k to be some constant, which I don't have to be too specific about because it's not critical how you choose that constant theta, divided by m, and m is the bound on the variance of the gradient estimate, divided by square root of k, okay? So it's square root of k, not k. So I'm going to analyze the case where you choose the steps like that. And what we're going to show is that the function values of this averaged xk iterate converge to the optimal function value in expectation at a rate of approximately 1 over square root of k. There's a log term here, but log terms don't really matter, okay? It's basically 1 over square root of k. So we can prove that. Now, instead of taking one slide, this sort of takes 2.5 slides, but it's still very elementary, so I thought I'd show it to you anyway. You can, again, use exactly the same logic that we had earlier to get to this expression. This is just a rearrangement of what we had earlier, okay? Now what do? I have to remind myself what's going on next. Okay, so we know from the convexity expression that this is true. Gi is a subgradient of f at xi, so I know that f of xi, it's on the true graph of f, so it lies above this linear approximation. Okay, so I can use that fact to replace this with a lower bound. And a lower bound on this quantity is simply f of xi minus f of x star. Okay, so I can replace this by this using this inequality here. Okay, now I'm heading in a different direction from what I did with the analysis of stochastic approximation, but just bear with me for a couple of slides. So now what I'm going to do is, again, a trick that I used earlier in the last talk, is I'm just going to sum from I equals 1 up to k, when k is the latest iterate. On the right-hand side, we get a telescoping sum, right? It's always fun to see because the alpha I plus 1 is going to or the negative alpha I plus 1 is going to cancel with the ai from the next term. So when you sum up this part, you just end up with a1, essentially. You actually get a1 minus ak plus 1, but we're just going to throw out the ak plus 1 because it doesn't change the inequality. So I can replace the sum of these with just a1. That's the biggest one, okay? And here's the sum of this from I equals 1 up to k, the sum of the alpha I squareds. On the left-hand side, we just get the sum of the expected errors in the function value from going from 1 up to k, okay? So carry that over to the next slide. Now, because expectations are nice linear objects, I can take the expectation outside the summation here, right? No harm done there. And then I can divide both sides by the sum of the alpha i's. That's all I've done there. So here was the original right-hand side. I've just divided by the sum of the alpha i's. Same thing on the left-hand side, except I've taken the expectation outside the sum. Okay? So again, very elementary facts about expectation. That's all that's going on there. Now I use convexity of the function f. Now you all know the definition of convexity of the function. Convexity of function f says that the graph of the function lies below the chord or the line that joins any 2 points on the graph. Okay? So by extending this idea, you can use the fact that the xk bar, which is the weighted average of all the xk's you've seen, the function value at that weighted average is less than or equal to the average of the function values. That's exactly what convexity says, where you use the same weights on the average. So this gives me a way to replace this object here with this object here. And that's all I've done in going from here to here. Okay? So now I've got a handle on the thing that I really want to analyze, which is the expected error in the function value at this average point. This is the thing that I wanted to get a bound on. And here is the bound. Okay? Now the game becomes, how do I choose the alpha i's? Or I've already told you how to choose the alpha i's. What effect does that choice of alpha i's have on the right-hand side? Okay? So what I'm going to do now is plug in the expression for alpha I, which is that it is theta over m times square root of I. Okay? I'm going to plug it in, and then I'm just going to do some clever elementary bounding on the thing that results. Okay? Okay, how can I bound this? In the numerator, we've got this term, sum from I equals 1 to k of 1 over I. How can I bound that? Well, you would recognize that that is, you can approximate that with a log. Okay? If you integrate 1 over x, you get log x, right? Integrate 1 over x, you get log x. And this is basically a discrete approximation to an integral of 1 over x from x going from 1 up to k. So you can approximate it with log x, and that's an upper bound, okay? So you can get an upper bound in the numerator. You can get a lower bound in the denominator by just taking, you've got a sum here from I equals 1 to k of 1 over root I. Let's just get a lower bound by taking the smallest term in that sum and multiplying it by k. The smallest term in that sum is 1 over root k. When I multiply it by k, I get root k. So this is a lower bound in the denominator. that makes the whole thing bigger. And going from here to here, we made the whole thing bigger. And now we're pretty much done. Because what can I do? I've done nothing. All I've done is to just express this differently. And I can see that I've got this log k over square root of k behavior. Okay? So we're able to show that the expected error in this average iterate is going down like 1 over square root of k. All right? For this particular choice of step length. Okay, so I wanted to show you the whole proof just to show you how that there's nothing magic going on behind the curtain here. This is all very, very elementary. Now, this isn't to pretend that all the analysis and all the literature for stochastic gradient methods is this simple. There are more complicated variants with more complicated situations like parallelism and so on, different choices of step length that give different analyses that are somewhat more tricky. But these are very fundamental, workable algorithms that you can apply, often get good behavior from, that have a very sort of transparent, simple analysis. Okay, I wanted to tell you about a different possible choice of step length because this again plays into when I come to talking about parallel variants of these methods, which, when did we start? 1:30. Oh, yeah, I've only got 10 minutes left. I guess we'll be talking about this tomorrow then, for the parallel versions of these methods. But we're going to use constant step sizes in that approach. And the two step sizes I've told you about so far are 1 over k step size and 1 over square root of k. Now I'm going to say, well, can we get an algorithm with provably good properties by taking a constant step, just like we did in short step gradient descent? Is there a place for constant step methods here? And the answer is yes, and the analysis is just as elementary as we had on the earlier slides, although different, okay? But, you know, same level of complexity. So the question I'm going to ask here, I'm going to go back to the strongly convex case, where mu, the modulus of strong convexity, is strictly positive, okay? Now we already have a way of getting a 1 over k algorithm for that case. I'm going to show you another way to get a 1 over k algorithm that uses a constant step size. I'm going to assume that you're going to tell me in advance how low you want to get the error to. In other words, I'm not going to assume that you want to potentially drive the expected value of the error, ak, all the way to 0. I want you to tell me in advance a threshold below which you want to drive ak. And then I'm going to choose the step size alpha to achieve that threshold in a reasonable number of iterations, okay? So that's our motivation. So again, I'm just going to go back 5 slides and pull out the expression that we proved a few slides back for the upper bound on ak plus 1 as a function of ak. This is exactly what I had earlier, except I've replaced alpha k by alpha because I'm now going to choose a constant step size. So this is just what we had earlier. Now I'm going to look at this and I'm going to say, well, now that alpha is bounded away from 0, there's no way I can drive ak plus 1 all the way to 0 because this term is always strictly positive, right? So there's no way that this expression, no matter how small I make ak, this expression is always going to, you know, have some positive upper bound. And it's not going to go to 0. Okay? So I'm going to look for the limiting value. How small can we make ak, given that we've always got this kind of constant jump happening on the bound at every iteration? I'm going to denote the limiting value by a infinity. And if the ak's are approaching a infinity, I can just take this expression and plug in a infinity for both ak plus 1 and ak, okay? Assume they both converge to this value. Now, I'm not giving you a completely rigorous derivation here, but this captures most of the flavor of what's going on. To dot all the i's and cross the t's, you have to be a little bit more careful. But this certainly captures the flavor of it. So I can get figure out what the limiting value is by just simply putting a infinity both here and here. And now I've got an expression in which the only thing I don't know, well, assuming I know the alpha, I can tell you what a infinity is by solving this equation for a infinity, right? And I'll tell you how to do that on the next slide. But before I do that, let me just compare this expression, which is the step-by-step expression, with the limiting expression. And now let me just subtract this formula from this formula. So I'm subtracting a infinity from ak plus 1 on the left-hand side. On the right-hand side, I'm subtracting A infinity from A, well, I'm just subtracting this from this, okay? Now when I do that, the constant term cancels, it's gone, all right? The first term is now the scaling factor times the difference between AK and A infinity. And what can we observe from this? Well, the AKs might not be going to 0, but the difference between AK and A infinity is converging at a nice linear rate. And it's converging monotonically, in fact. So we're able to say something about the rate at which AK is decreasing to its asymptotic limit. Okay? And in fact, you can just apply this recursively, and you can show that the difference between AK and A infinity is less than or equal to this constant raised to the power k times the initial difference. Okay? So hold that thought, and what we're going to do now is just evaluate A infinity explicitly from this formula. Here it is here. I just took A infinity over to the left-hand side, divided by 4 times mu, and I got this formula here. Okay? Now I'm going to use that, and I'm going to plug it into this formula here, all right, to get an upper bound on AK. So I'm going to take this A infinity over to the right-hand side. I'm going to substitute for A infinity from that expression, and I get this, okay? A infinity's gone to the right-hand side. And what have I done here? Oh, all I've done here is I've dropped the A infinity from here because I can do that and just make the thing bigger, okay? So I've just got rid of that altogether. All right, so now I'm going to now look at this and say, how can I choose the alpha so that this is driven below some threshold epsilon within a reasonable number of iterations that I'll call big K, all right? So here's the answer. I'm sort of cutting to the chase here. My claim is that if I choose alpha to be 2 times epsilon, epsilon is the threshold that I want to achieve, times mu, the modulus of convexity, divided by m squared, and if I choose k, given that choice of alpha, I choose k to be this, m squared divided by 4 mu times 4 epsilon mu squared times the log of this quantity. That's going to give me reasonable convergence. Now, I'll analyze this on the next slide. It's just one slide of analysis, but let me observe before I go there, this is kind of a 1 over k rate. Okay, the number of iterations, big K, that I need to achieve a certain level of precision epsilon is like 1 over epsilon. Okay, so in order to get something that achieves twice the amount of precision, in other words, if I replace epsilon by epsilon over 2, what happens to the number of iterations K? It goes up by a factor of 2, right? So you get sort of a 1 over K behavior here. So this is bona fide 1 over K, I'd say. All right? But you need to know epsilon. You need to specify epsilon in order to define these quantities. Here's the analysis. Okay? Here I'm verifying that the expression for K is right, given the choice of alpha that I've made. All right? Okay, so given the, okay, here's how I choose the alpha first of all. Here's the motivation. I want AK to be less than epsilon in the end. So I'm saying, okay, that means that I'm going to achieve that by making this term less than epsilon over 2 and this term less than epsilon over 2. I just divide the pain equally between the two of them, right? To make this term less than epsilon over 2, this is how I choose alpha. Very, very simple. There's no K here, right? So I just choose alpha to make, you can easily see that if I plug this alpha into here, I get epsilon over 2. So that part's really easy. Now, I can plug that alpha into this expression and ask the question, how big do I have to make K to make this term less than epsilon over 2? And that's what's happening on the next slide. I'm just figuring out how big do I need to make K to drive this term below epsilon over 2. And you can take log of both sides, you can use this lower bound on log, you can just divide both sides by this quantity. Again, incredibly elementary, and you get this lower bound on K, which is exactly what we had on the previous slide once I substitute for alpha. Okay? So again, nothing mysterious here. Something you can do in using only very elementary tools from math analysis. And one point I want to make about this is that it doesn't hurt us so much in this You remember I said when we were doing the basic form of stochastic gradient, that if we underestimated mu, we could get a dramatic deterioration in the behavior. That's not true of this in this case, in the constant step size case. If you make a mistake underestimating mu, the price you pay is that you get you pay a pretty modest penalty in the number of extra iterations you need. Okay, so let's see exactly how that works. Suppose I get mu wrong by a factor of 5. The effect of that is that I'm going to misestimate alpha by a factor of 5. So if I underestimate mu by a factor of 5, alpha is going to be too small by a factor of 5. But the number of iterations I need is only going to go up by a factor of 5. Okay? Now it looks like it's going to go up by a factor of 25 because I've got a mu squared here, but that's actually not true, because if you work back through the analysis, one of these mu's is the true mu, and the other one is that you use to estimate the alpha. So the number of steps that you need is going to go up linearly with the amount of underestimate. So there's a fairly mild performance penalty. So the pro of using a constant step size is that you avoid average, you still get the 1/k convergence rate, and you don't have the sensitivity to your estimate of the modulus of convexity. The con is that you need to know mu, you need to know m, this upper bound on the variance, and you need to, if you really want to know when to stop, you need to also estimate the initial error, okay? So you need to estimate all these parameters of the problem before you can actually know how to choose the step size. So in practice, of course, you have heuristics, or you might have some adaptive way to choose all these quantities and to make successively better guesses. But I particularly wanted to mention this approach because tomorrow when I talk about parallel stochastic gradient, this is the kind of scheme that we use, and our analysis of this case is based on the elements that I just showed you here. Okay, mirror descent, I'm out of time, so I'll pick it up here tomorrow, but I'll just make the point that mirror descent is just a generalization of exactly the averaging approach that I showed you earlier. So I have a few slides on that. I'll run over this stuff. When I do it, I'm going to go over it quickly because I noticed that Stan Osher is giving some talks later this week. Stan Osher loves this stuff. Bregman divergences, all that stuff. So he's going to tell you about this in, I better not say anything bad because he might watch the video. He's going to tell you about this in great detail, okay? So I don't have to go over it in tremendous detail. And that'll bring me to the end, and then I'll start talking about parallel SGD. I'll spend a few slides on that. Okay, but I have to quit here, so maybe there's time for a question or two, and then we'll take a break. All right, thank you very much.